All right. Uh, are we good to go on the AV? All right, folks. We're on time. Let's get going. Thanks for coming. Who I put some things here on the slide just so you know if you wander in the right talk. Who thinks these are crabs? Right? Few hands. Yeah, more courage. You're wrong. Uh, so these are what they call porcelain crabs, and they resemble true crabs, but they're mostly related to lobsters and hermit crabs. So not they're fake crabs. So in nature, there's actually a process called carcinization. You had the word in the title. And that's a sort of a form of convergent evolution where we're sort of non-crab things want to turn into crab-like things. So I think you see the connection here. Um, all right, so it was coined, I love that quote, like the many attempts of nature to evolve a crab, right? All right, so thanks for coming. I know there's literally a talk in the other room promising you that you can change the world. So if you came here, you know why you did. So you came for some pain. You didn't come to change the world. Let's face it. So in general, when Rust folks are looking into C++ or C Interop, it's sort of more or less natural because they need to call into some library or some functionality that they don't yet have natively in Rust. So kind of they have to, right? But when C++ folks care about Rust Interop, then I think some degree of desperation is involved. So don't throw things at me. You self-selected to come here. Uh, so so it is what it is. Um, all right. So Rust code everywhere is increasing at an accelerated pace. But so does C++. And that's sort of on top of gazillions lines of C++ out there. And even today, there's more C++ being written than Rust. But hybrid code bases are here to stay. They're becoming the norm, whether we like it or not, with all the complications, all the problems that come with it. I don't think there's a turning back point, right? We passed that. So we kind of have to figure out how to navigate this place together. And we need to learn to play nice, like for a long time, right? This will be the place where we live. So because we're right after lunch and probably you're getting sleepy and sluggish, I'm going to do gymnastics and sort of ask you to raise your hand from time to time, right? So when you talk about Rust interop, probably you think about CFFI things, right? You think about glue code, some kind of code generators, and maybe some kind of fat compiler that can do both, or linker things and ABI things, right? And all of the above. It's like a soup of nasty things. So what are you gonna get out of this talk? I'm gonna survey the major interop challenges right now, show you some of the solutions and experiments and even things that people use in production out there, sort of the existing status quo, with their problems and limitations, with their strengths and so on. And I'm going to tease out some avenues of research and pursuit in this area. So, and it all sort of is framed by the fact that general purpose high fidelity Rust C++ interop has yet to be achieved. So just we have many solutions that kind of make it work, but like many of us would realize when we sort of do this for real, just beyond some toy experiments, is that just making things work, it's not going to cut it for this space where we operate in the native systems programming space. So a lot of these solutions sort of fail to deliver on the promises. So it's going to be roughly a story in 3 parts. Attack of the CodeGen, the ABI menace, and Beam Me Up Scotty. Sort of for all tastes, let's say. So I don't split the room necessarily. I'm a Trekkie myself. So I think the problem stemmed from the fact that both C++, but Rust as well, maybe even more so, have an extreme range of operation in industry, right? From the smallest chips to web applications and services and all sorts of things, right? So it's because of that span, the needs and what people expect in terms of this interop story are wildly different in terms of priorities, completeness, requirements, performance, and so on. So in general, when you ask people, they would sort of tell you all sorts of top things, top of mind things in this space. So I don't want to pay for performance overheads. I don't want to deal with over boilerplate annotations and all these things. I want broad type availability. I don't want to sort of narrow myself to something with loss of semantics. Avoid lowering to C. Ergonomics with safety. Yes, I want to eat the cake too. And working with dynamic libraries, why not, right? Some of us live in Windows world. ABI considerations, how things work, stability, and so on. I'm going to talk a lot about this. I want things to be easily automatable. If I have to do everything by hand, it's going to be unappealing. I want to debug this hybrid mess, right? Have the ability to have mixed stack frames and reason about them. And I'm not going to even touch about engineering systems in general. I've done previous talks where I talk about sort of gradual Rust adoptability in a company, challenges with engineering systems, and so on. That's a whole different other topic. But that's important as well. So I truly believe that making this story work is dealing with all these pieces. Just focusing exclusively on one of them, like, oh, just the compiler, just the language part, or just the ABI part, it's not going to cut it. So it's really a story of all or nothing. So this is the Rust C++ Interop talk. This is some of the places where I've done damage in the past, and a few ways to shout at me if you really want to. And just as a disclaimer, just like if something I say sounds like a hot take, probably is. So take it as it is. So let's start with what's out there. And I'm going to show some code, but before I do that, because we live in weird times, I have to put out this disclaimer. So all the code you're going to see, it's not much, but at least it's artisanal. So all mistakes are mine, just a human agent, humble. So no hallucinations, but admit for errors and hot takes. So let's get into it. So the original duct tape in this story is C, the lingua franca of all interop, master of everything. It's the first thing that comes to mind when you think about FFI, right? Every API consumable out there sort of has a way of going through this interop language. This is the only sort of ABI stable universal interop glue out there. But as we quickly learn, it offers poor abstractions in many situations, almost no safety, naked structs, public fields only, row pointers, you know, the story. I don't have to sell this to you, right? And by the way, this is not going to be a why Rust talk. I think we started the conference with a very good talk about why Rust. So I'm going to tell you, okay, you are in Rust world, so now deal with it. So I'm in the sort of sad realization part of the journey. So I think most of us heard about bindgen, right? More than half of the room. Cool. So this allows Rust code to call into C APIs. So you can easily turn C headers into Rust FFI bindings, sort of similar to what you see, the toy example you see there on the screen. So it sort of requires a source generation build step to get through this. And it's sort of a unidirectional thing, right? You see that ReperC business there. I'm going to talk more about that later. So more or less sort of unimpressive things. Right? Gets the job done, no frills solution. If you want to go the other way, right? C code to call into Rust APIs, right? Turning .rs files into C headers. Symmetric solution, almost. Again, nothing surprising here. Source generation, build step, nothing interesting. Probably you're bored by now. So let's sort of put them in the same bucket and talk about what they offer. So one advantage is that you operate directly on source files. You don't need to go through some kind of intermediate representation or IDL file. They do require builds system orchestration. You do have to be limited to a C ABI as a foreign ABI representation because Rust. So I'm going to talk more about that in the middle part of the talk. And you only get pass-by value for just C types, right? And I'm going to stress on that a bit throughout the solutions out there, because really pass-by value is something you want for performance. And I'm going to talk what it means to put stuff on on the stack, and when you can and cannot do that, and when you can and cannot move structures around, right? So you can't do structs with private fields, can't do C++ classes, obviously, right? No fancy memory management handles or boxing types, no Rust enums, boo. No string slices, no slices whatsoever, right? Because even slice representation is not guaranteed in Rust, right? There's current ongoing efforts to properly define the representation of a slice. You know that conceptually in your mind, you know what a slice is, right? And you can even look in the implementation to see what it is, but there's no guarantee that that's the actual representation. There's no commitment that that's the representation. So there's ongoing efforts to sort of formalize that, so that at least you can count on something. More about that later. So lots of complicated, unsafe Rust code that you need to write in order to convert to from this C representation. So some scaffolding required, but some of it can be automated. So not great, not terrible, right? And many projects just go by with this. I'm not trying to say that, oh, never do this. If this is all you need, do it. It's good. It's a proven technique that many projects actually use in production now. But if you want to sort of raise the level of semantic and abstraction and sort of literally do C++ interop, not just C, then there's this the CXX crate. And this is a solution that is more opinionated, but it tries to operate at C++ level. And it does go through a macro-based ideal. You can see it right there in the top box, how this ideal would look like. You have this special FFI module that you need to define in the IDL. And by the way, the funny hash thing there is just macros in Rust. And that's how you do sort of source level magic. So it needs, this ideal file needs to be separately maintained manually, right? But again, here you get to be more surgical about your interop types and sort of what's your boundary of interop. As in, you put in the ideal file only the types that you really need to marshal across this boundary, right? So not everything becomes immediately visible on the other side. That can be an advantage, or not. You're going to see that later. So from this ideal file, the generator will spit out representations on both sides. You can see the Rust and the C++ bit. So you can deal with almost all standard types, slices, yay. Everything you put in the IDL, all your custom C++ classes, you can have unique pointer and standard optional, and the equivalents of box and option, string slices, strings, vectors, everything you want, right? So it's sort of, it's like, oh, this is like the complete package, right? And for many people, it is. Like, I think in many people's minds, this is sort of synonymous with Rust C++ interop, as in when you tell them about this, like, oh, this is a solved problem, cxx.rs, like, I know this. This library had to make some trade-offs, had to make some calls, like, and it's intentionally restrictive, as in the things that it claims it supports, and it supports well. So it's restrictive and it's opinionated, as in it made some choices and how it maps semantics from one language to another. And if you don't like it, sorry, this is not configurable, right? And one other thing is that CXX doesn't know about the memory layout of the user types, right? So, and because of that, you cannot do pass-by value. So you need to box things around. So that's a major disadvantage. And also sort of a consequence of how this works is that you have to rely a lot on pinning. How many people know about pinning? This is not a Rust conference, so I have to ask. So just maybe a third of the room. So for the others, so pinning in Rust allows you to maintain a stable object. something happened there. Okay, so allows an object either to remain stable in terms of if it has self-referential things or internal pointers for foreign consumers, as in it sort of literally pins it in memory, because otherwise Rust likes to move stuff around, right? So this is not something you expect on the other side. Because of this, the library requires pinning, and pinning tends to pervade the boundary of interop. And whenever you have pinned code, it tends to be less Rust idiomatic. It's definitely not ergonomic in use. So it makes things uncomfortable. It works, no problem with that, but it sort of feels like I have to work against it. It pollutes the code a bit. It's uglier, but at least it works, right? But again, there are situations where you, depending on the kinds of libraries and APIs you have to interact with, you might have to deal with callbacks and allocators, and then it becomes painful to the limit of impossible. Again, depending on your use cases, this library might be exactly what you need. And if that is the case, go for it. It's proven, it's solid, it's been around for a while, it's used in the industry. So again, if your needs align with this set of trade-offs, like you're gonna see each solution that I'm gonna show has made some choices, right? And if those choices align with your project needs, then it's great. If not, this is where it's gonna be tougher for you and me. So another solution that is less known is Zengar. How many people have heard of Zengar? Literally no hands. Good. Then I have something to talk about. So this is a newer interop solution. Again, relies on some custom ideal thing, that Zengar file that you see on the right box. The difference here is the thing I put out in red there. This ideal file allows you to specify layout of your structures in terms of size and alignment. And this becomes important because now providing this information in the ideal definition, then you get to know, okay, now I know the layout of the structure, and then I can pass it by value. I can put it on the stack and stuff. Again, from this ideal, you get the generated things. Again, I don't think the auto-generated code is surprising in any way. So custom ideal, again, same problem with all ideal files. You need to manually maintain it, update it, and so on. You get access to all the standard types, mostly. Slices, everything you put in the ideal. Because of the size and the alignment definitions in the ideal, you can pass by value. So no more needing to box everything and in directions and heap allocations. So it's much more efficient in most cases. No more need for pinning. Most cases you can just get away without pinning. And sort of it's a more ergonomic to use in most situations. And only occasionally you will pay for runtime costs. There are many sort of corner cases where you have to do more like CXX kind of things. But in general, it tends to be more flexible, right? It's a bit more involved. Maybe it has a bit more knobs than most people are comfortable with. Maybe more people are comfortable with the simplicity of CXX, and they're happy with the trade-offs that the designers made. This one is sort of in the I'll let you control more things kind of camp, right? It's a younger framework, so less industry adoption and sort of less years in production, so to speak. But it has a lot of promise, and I see a strong interest from a lot of companies sort of to invest to push it further. Another one is Qubit. Who heard of Qubit? Again, no hands. Great. Literally great. I get to boast about it. This is a very new project with the goal of high fidelity language interop between Rust and C++. If the others you saw before were in the, okay, let's provide the most common things that I think you're gonna need or most people would want and just ignore the rest. This has a goal of high fidelity mapping, as in We want to support the world, like every crazy thing you can do in C++, even templates, right? We plan to support it. It's not there yet. Don't get too excited. I said it's a new project. It's only been like maybe a year and a half in development, but it's an active development. So there's a lot of wind behind it. Google is pushing this project, by the way. So it's not some kind of lone developer somewhere in Nebraska, right? Because it aims for this high fidelity mapping and sort of understand everything that crazy C++ can offer, it needs deep compiler integration. And right now that the implementation sort of assumes Clang plus Rust C, right? Well, on the Rust side, there's no sort of ambiguity at this moment because of sort of monocompiler culture. But on the C++ side, if you're not in Camp Clang, then not yet. More about this very soon. So it works directly on source files. So there's no IDL involved here. And the objective is that, oh, I have this big C++ thing. Let's say I have like 1,000 functions in the API, and I just like want to blindly map everything to Rust. So, and I don't want to sort of maintain duplicated API definitions for my 1,000 function microservice. Remember micro in there, right? Anyway, people need that. So it covers the whole API surface. So it's not about like being surgical like with IDLs. And no compiler diversity yet, right? There are plans for an optional IDL. I'm gonna show what that means in a later slide. But it's not right there. So if you jump right now, just Clang, be aware. Even though it doesn't have an IDL like Zengar did with the layout annotations, because it has deep compiler integration, it can actually query the compiler for layout information of your structure. So it has all the information out there on both sides. So that means pass by value, all the things, good. Performance, good, right? And sort of on the top is the current situation in implementation. So let's say from C++ header API goes through Krubit to get the Rust API. And the plan here is to eliminate this Clang coupling by introducing this optional IDL in the future. And that would allow you to bring your own compiler. And if you teach and have like a layer that adapts, like sort of a bridge that adapts from, let's say, GCC or MSVC to produce this IDL, then you won't have to rely on Clang necessarily on the C++ side. So it's not there yet, but there are plans in motion. So all the things that I showed until now, sort of, they made some choices somewhere in this spectrum. From on the one extreme, you have the toolchain agnostic, specific API bindings things, requiring API stability, having some sort of story for version resilience, having support for dynamic linking, and so on. And at the extreme other end of the spectrum, we have tight compiler integrations, better ergonomics, bindings for all APIs in the surface, so no need to manual fiddle with definitions. But you sort of rely on this sort of unstable API story on sort of being in the camp of compiling everything from source. So if you're closer to that end of the spectrum, solutions like Krubit can fit better in your home. Whereas on the other side, things like CXX and Zengar can be a better fit. So it's a trade-off slider. And even Krubit is sort of, as it evolves, it sort of tries to get closer to the left. But it's difficult, and I think the difficulties come from impedance mismatch in language semantics. And we like to think as Rust and C++, they're in the same kind of camp of letting me access hardware and memory and being close to the metal and native languages and sorts, but there's so many semantic differences, and I just enumerated a couple of them here that make life for Interop really, really hard, right? For example, these are C++ features that have no correspondence in Rust, as in direct translation. So it's hard. There are profound differences. So I'd say, even if it's not entirely true, I would say that Rust semantics tend to be a subset of C++ semantics, with some small exceptions, because Rust in general is less expressive, or dare I say crappy. So because of this, using Rust code from C++ is easier, while using C++ code from Rust is much harder. So if I would split them in two slides here, is like calling C++ from Rust, really hard nowadays, especially if you're like want to call everything in C++, like don't. So there's no correspondence. One concrete example is overloading, function overloading. Like if you need to disambiguate between several function overloads in C++ from the Rust side, that's like hell at this point, right? So it generally tends to be unsafe, very difficult to deal with lifetimes. There's proposals in flight right now for some kind of annotations and additional types in Rust to help with this business, but they're not here yet, right? It's just vaporware at this point and proposals, RFCs. And there's no strong consensus behind them. So don't like say, oh, it's an RFC, it will happen next year. We don't know. Dealing with aliasing and aliasing references, generally hard, or at least proving properties about them is very hard. And I'm going to talk a lot about movable types. The other direction, much easier. Literally, you can do it today. No big ceremony here. So Rust semantics as a subset of C++ semantics. Because Rust has a really strong type system, you don't have to guess as much in these Interop bridges. You don't have to infer and have some kind of heuristics. You can be very certain about the semantics on the Rust side. Because of that, there's less ambiguity. Also, querying Rust C compiler, although the Rust ABI, the internal representation, is not stable and is not guaranteed to be the same from version of and version of a compiler, like literally from today to the version from 6 weeks from now, there's no guarantee that it will be stable. So you always need to refresh these queries with each compiler version, hence being at the opposite end of the spectrum that I showed. But you can at least get structure layout information, struct fields. You can even infer mapping of special member functions from key trait implementations. You can literally see, okay, this type implements these traits. And let's say, oh, it has a drop trait implementation. I can map that to the C++ destructor or clone and so on. So there's more stuff that you can query and prove reliably rather than guessing. So I mentioned function overloading. I had to pick one example here. So some folks who are actively involved in this effort claim that we really need to have a way to semantically identify C++ overloads from Rust at the core language level. And that means modifying Rust language to support this or to account for this, at least optionally, right? I'm strongly in the opinion that we need to resist this temptation to complicate Rust just for the sake of Interop. One poster child of this route is Carbon. Chandler, who is around here at the conference, by the way, did a very nice presentation at RustConf 2 or 3 weeks ago, explaining how Carbon deals with C++ Interop and the trade-offs that they made in the language design to account for this. So they're very much in the let's design Carbon to map as closely, like glove-like, to C++. They made deliberate choices there. I don't think Rust needs to be in that space. It's definitely not there now, and no appetite to get it there in the community. I think we can probably solve this outside of core language. No need to hinder, by the way, messing with overloads on the core language side in Rust would destroy a lot of the power of the type inference system. So it would become much harder to do type inference. And if you think about it, at ABI level, overloading effectively doesn't exist. So it just differently mangled stuff in the names. So I don't think there's a fundamental need to mess with this in the core language. We can probably deal with this at the ABI level in tooling, in compilers and linkers. So I'm not in the camp, but you're gonna hear diverging opinions. There's people who lobby strongly that we should get Rust closer to C++ in this space. So the ABI, I promised more about ABI. So what is ABI about? So this, many people think this is something to do with the language itself. It's not. It's about the system, the tool chain, the platform you're targeting, and compilers play a role in this, a big role in this, of course, but it's definitely not about the language itself. People like to talk about ABI stability, right, and when to get there. And it's never a comfortable conversation or satisfying conversation, because there's no good moment to say, now we want to freeze the ABI, right? That's why Rust doesn't want to do that. They like the freedom, because they say if we stabilize too early and commit to something, then we shut the door to fix things, right? It's never a good moment. Like, there's lots of reasons why you want to have this flexibility. But at the same time, there's lots of reasons to want stability, or at least have some contractual way in which you say, okay, for this part or for this version, I want to guarantee that this is stable and I can reason about things in binary representation, right? So for example, when you don't want to share the source code of your library, I know, who would think? Or you cannot use the most recent compiler for your library, or you want to mix and match, have different compiler versions, build different parts of your system. Yes, people do that. When you don't want to recompile the whole world, again, there's many people for whom the story is, oh, we're just Bazel everything, like compile everything from source and build like a 4 GB monolith file from everything. Like, perfect. If you're in that space, things are much easier. But if you're in the space like, oh, I have to get this library from this vendor and this library from this vendor, and I have to sort of Lego them together, much more difficult. And the ability to ship and update components independently. Think about let's say in your mobile operating system, like want to patch a particular binary and not patch a ginormous payload. And share, why not? Yes, share libraries, plugins, and Interop. And we've done this like many many times, right? Maybe the original Interop story is COM. Like I see some older folks in the room, and it's not exactly new, groundbreaking thing here. Like we've done Interop for 40-something years in different ways. Like, so more modern incarnations, and I think a good example to follow here is Swift. I don't know how many of you are familiar with Swift, or if you even care. I see a couple of hands in the back. Even if you're not, I would still think there's a lot of value to just look over the fence and learn from what they do, right? There's a very good presentation from Doug Greger there that talks about ABI stability and resilience, building resilience in the Swift standard library, and within library evolution in mind, as in I want to have the flexibility and the ability to evolve the library and fix mistakes and improve it, but I want to offer resilience guarantees to consumers. I know it sounds like they're opposing goals, but I'm going to tease out some of the tricks that you can play to deal with this. So the ability to control where you are inside the boundary of resilience. Highly recommend that you watch that talk if you want to like deep dive into the topic. It requires no real Swift knowledge, so don't feel like, oh, I can't watch because I know nothing about Swift. It's very approachable and very well constructed. So let's sort of try to tease out how this would look for C++ and Rust, and drawing heavily as inspiration from the Swift model, right? So again, remember those ideal layout representations that we had to manually put in Zengar. we can rely on the compilers to query that information for us. But the idea is that you don't want to do this in a way that costs, in a way that sort of hurts runtime performance. You want to do this as efficiently as possible, right? So only do it when it's absolutely necessary, and do it as little as possible or as efficient as possible. So what you want is you want to expose this metadata out of the compiler. Everything related to size, alignment, strides, overlapping, padding, all these nasty bits that will cause problems when you try to map from one language to another. You want to have all these nicely packaged into some kind of payload metadata, right? And you want the compiler to synthesize this for you. You don't want to do this by hand like you have to do in Zengar. So this is where, because of performance considerations, we need to draw some clear boundaries around what we're trying to do. As in, we need to differentiate between library code and client code. As in, the distinction is not necessarily about who calls whom in the contract. The distinction is about what pieces are compiled always together versus what pieces might be sort of external or out of our control. As in, if I'm providing a library, for example, I know that my library will be compiled as a whole, right? So inside the boundary of my library, I don't want to pay for any of this business, any of this mess. I want to have maximum performance, right? Again, on the client side, everything inside the client, it's compiled together, right? So I don't want to pay for any indirections in that bubble either. But wherever there's a cross between the two parts of the system, right, then I need this resilience, because I don't know if the client and library will be necessarily compiled together or not, right? So when a client tries to access a field, let's say from a library or structure from a library that I provide, it needs to read this metadata and to find field offsets and do some arithmetic computations to figure out, okay, where's this place in memory and how far apart and whatever, all this business. So it needs the metadata payload, and it needs to do some arithmetic indirection to get to it, right? That's the sort of the costly part. On the library side, you can just skip the indirection parts, the things that I have grayed out and crossed, right? You don't need to do those because you know exactly there. You're exactly there. You're like normal code, right? So you can skip all these indirections to not eat up your performance. And of course, dealing with dynamically sized things, I won't go into the details here, but I left some of the caveats and delicate parts on the slide for you to analyze later. So again, it's about managing these boundaries, managing these indirections, as in just a super simplified picture here of where are you in these boundaries. And I see this as a frequent mistake when people do interop, is they do opportunistic interops, as in, oh, now I need to call this, and then I'll rewrite this piece, and then I'll rewrite more of it. And no, you need to be very deliberate about the pieces that you carve out to say, okay, now I'm going to rewrite this part in Rust, or now I'm going to introduce this new component in Rust. As in, the boundaries of interop need to be properly chosen so that it's convenient and they make sense for how you compile, for how you consume, for the width of the API surface, and so on. So they need to make deliberate choices. And again, if you carve these pieces correctly, architecturally in your system, as best as you can, it's never ideal, then you can control these resilience boundaries and you can say, okay, I'm paying the cost only when I'm crossing the boundaries, not within the bubbles. So this is sort of the summary of what I just said. Okay, so now I'm going to move to talk about padding. I assume everyone is sort of familiar with padding. I know who's familiar with tail padding specifically. Tail padding. A few shy hands. Don't worry, I'm not going to put you on the spot to say what it. So the tail padding is just padding at the end of structures that is used for nefarious purposes. And for that, I mean optimizations, of course, not like hacker things. So I'll give just a few examples. For example, C++ is allowed to reuse tail padding of structs for various purposes, and this is not allowed in Rust. And as you can imagine, this can cause problems. Rust treats tail padding as part of the payload, right? And very much expects that memcopy of size of t bytes, that's what the type is, right? That's what the payload is. Whereas with C++, that's not the case. C++ does not allow you to make such assumptions, right? If you do, it can work, but not for all t's. So, for example, fields of a child class may be placed in the tail padding of the base class. Mind blown, I know. For another example, a field with no unique address may have its tail padding reused for the neighboring field. Think about sort of lining these things one after another, right? So just a few examples, right? So this prevents a Rust program from turning a C++ child reference into a base class reference. And because if you would do that, you would just override the tail padding of the child. So that would just be recipe for disaster. And if your types are just plain structs, it might just work and you don't even notice, right? But in the most general case, doing so, it's undefined behavior. So there's several ways to mitigate this, and they're not all there. So in general, people think they can just get away with this, as in say, oh, I don't care about how Rust sees things internally and what's the internal API, and I just know that, okay, whenever I need to talk to C++ or C, I'll just go through this business, right? Or like I'll just request a C API, and that would solve all the problems. Well, they will solve some of the problems because the status quo is sort of the only instrument in the toolbox that most people use, and you've seen this, by the way, in those generated files coming out of bindgen, cbindgen, and CXX, right? They're limiting you to some of the things that can be safely represented in this universe, right? And you've seen that it really restricts the vocabulary of things that you can talk with. I would very much like to be in a world. Next two slides are just fantasy. Don't copy everything and try it at home, right? In a world where I can have this kind of ABI variants that are opt-in, where you can talk about more things in a native form, like slices and enums and all sorts of things that are sort of feasible at the API level, like high-level semantical things that are becoming available, like and even sort of at crate level things to expose. So these are all, like I said, fantasy slides, but if you like any of the purple things you see on the slides and you would like to say, oh, I want to discuss this in a portable, ABI portable way, well, that's sort of the future that we need to aspire to. There's all sorts of tools and validators that can check compatibility, and you can make those parts of your workflows to enforce and say, okay, let me check if the ABI representation is broken. Like I made some assumptions, and then when I upgrade toolchains, I want to see, oh, does it still match? Does it still work, right? So there's all sorts of tools like ABI Cafe and Krabi and other things that can help with the process, but they're by no means sort of mature enough or standard enough that people rely on them. They're more in the fringe space. So this is an area of strong interest, but it's very much not a solved problem. Another part of the discussion is object relocation. So one particular sensitive topic about handling C++ values is that in general they're considered to be non-relocatable. As in, and by that I mean if I move the bits in another part in memory, I preserve its invariant and sort of Brazilian to be moved. Right? This is generally true, but assumed not to be true in C++ by default. And that sort of harms the interop story, because in Rust it's the other way around. So this generally hurts everyone, and there are actively efforts to formalize this business in C++, so you can actually rely on it rather than trick take advantage of it. So there are a couple of scenarios where it's really not true, right? When you have some kind of internal pointers on observers or some sort of self-referential structures, and you know when you have to do this business, where you have to manually implement move constructors, move assignment operators, and such. But most types don't need that business, right? And the assumption is that all types should need it, right? That's the tricky bit. Okay, so there's a strong need for a destructive move on the C++ side. And a lot of even standard container types make these assumptions in a let's say, blessed way, right? They play tricks on optimizations, assuming they can do this, but it's in no way a formalized thing. So technically, they're sort of you being inside themselves, but it's okay because it's standard library. So the effort of talking about trivial relocation in C++ 26 standard is just a means of standardizing existing practice. This is not alien technology. We've been doing these kinds of exploits. We just want to legitimize them and have a way of expressing them in user code as well, not just standard libraries. So that's how we get trivial relocatability in C++ 26. There's a link there to a paper. It has 46 pages about a tiny trait. I dare you to read it. If you don't, I think I have 3 or 4 bullet points that will deliver the gist and not the whole trauma behind the paper. Really, there was plenty. It's all about the ability to do this mem copy, to move stuff in another part of memory, and then preserve invariants, and then have the ability to reason when is it safe to do so about a custom type, right? What are the rules so that it's not undefined behavior? And these are the rules, right? Don't try to parse the slide now; it's not necessary. But I have put it there, and just you'll get the slides for reference. So that would save you for reading the 46 pages. Problem is, why is this relevant in this discussion, is that C++ and Rust make opposite ways of handling moves, right? Rust likes to move by default and does mem copy of the bytes of t, regardless of t. And very importantly, it renders the move from object inaccessible, right? Which is not true for C++. And C++ likes to copy by default. And even when you do move, you need to have these patch-up functions like the constructor, move constructors, move assignment operators, right? Because you can't just mem copy things, right? Think one example is like standard string. Because of small string optimization, in some implementations you have a pointer inside the structure, right? And that's why you need to patch up the thing. You can't just like mem copy it. And of course, leave the moved from object in a non-destroyed state, so you can still refer to it, you can still sign to it, you can destroy it, and so on. So this comes in and can affect the interop story in subtle ways. And of course, you have to use the pin. I mentioned the dirty pin. So that's why before we had trivially relocatable types, you couldn't reason about placing a C++ object on a Rust stack, right? That's the tricky bit, right? With C++ 26 trivially relocatable, if such a type is trivially relocatable, and most plain things will be, then you can reason about putting C++ objects on the Rust stack and have efficient Rust interop. There's a very good paper by David Sankel there, if you want to read, like it goes in depth with examples and everything. I don't have time to allocate for this, but you can read it if you're into this sort of business. I think the paper there, it's shorter and much better explained than the paper that I mentioned earlier in the standard. So really what we need is something like a destructive move in C++. There's a way to fake it now if you're impatient. There's a move it crate. I don't know if you're familiar with it. It offers some nice tools that you can use to deal with in-place construction of C++ and Rust things. So if you need, just look up the docs for this crate. They're pretty well written. It's not a complete story, but it's a nice crutch that you can use in the interim. And uh, because sort of this is very close to the work I do and what I care about, I need to talk about the compiler side of things. I work on compilers. So most of the tricks I showed here, they do require some kind of compiler involvement, right? On the Rust side, it's fairly easier. Um, on the C++ side, it's a complicated story because it's very hard to get alignment. How compilers deal with this, the internal representations are very different. It's going to be very hard to get alignment on the C++ side. There's some appetite for ideal-based solution generators in an automated fashion, but it's no means a sort of an achieved consensus yet. Right? There's efforts in this direction. More about this in a few slides. So high fidelity language semantics and mapping of vocabulary types, like when you have requirements that most things just work, will require deep involvement from the front ends, right? And if you want to talk about toolchain independent IRs, I alluded to about this in Qubit earlier. Qubit has a specific IR it has defined for the representation, but that doesn't cleanly map to something like GCC or MSVC. So there's more effort needed here and alignment from vendors to get this working. And we are talking, but it's not moving as fast as you would hope. Some support libraries and sort of things that can help in this process and offer the wrappers that you would need in the consumption part are also sort of ongoing effort. So, and in the back end, again, I talked about the ABI issues and how to deal with padding and all sorts of, there are more things that I didn't launder here in public, but it's a long and involved story here. And compiler generators in the backend also need to be involved in this story to make it really smooth. I don't know if anyone saw the keynote from CPPCon from last week. Herb Sader had a really nice talk about reflection. And one of the use cases was actually to use C++26 reflection as a language generator. So you can generate bindings in any other language from C++, sort of in an attempt to make C++ the new lingua franca of Interop instead of C, using reflection mechanisms. I put a link there. It's already on YouTube, so you can watch it. I think it's a really neat presentation. So if you have an appetite for these kinds of things, do watch it after that. So in the Rust C++ Interop, there've been like this year really I think this was been very effervescent year for these kinds of discussions. Lots of interest in the industry. Big companies have pulled resources together. Independent people from the community. We had a bunch of meetings on the topic. There's strong interest to have this as a sort of cohesion and work on this more. I think we just got started, but I'm super happy to have it ongoing, right? We had a 25H1 Rust project effort aligned around the story, trying to identify the scope, map the solutions out there, contribute to the existing crates and solutions to see how we can improve, identify the gaps, the needs, and so on. Some of the things I enumerated earlier. As medium-term goals, we want to improve the ergonomics of the solution and document the space better. And of course, what I mentioned earlier about compiler vendors, getting some kind of alignment behind goals and priorities and needs in each company, because very much this story is backed by big company needs in gradual Rust adoption. So they sort of have to see where do we overlap in priorities and needs, so we can pull together and collaborate. The Rust Foundation even has delegates that joined the C++ committee to sort of try to bridge this gap in a formal way, sort of champion papers that help. See trivial relocatable paper as an example where both Rust and C++ people have been involved in the discussions, sometimes in unproductive ways. So some names to look for. Probably a bunch of you know David Sankel from C++ world. He's very much a double agent right now, just like me. So I already linked to write-up from David earlier. We had a bunch of meetings, and if you care about getting involved in such effort, we do have a Zulip server for the Rust project and a dedicated channel about Interop where it's not high traffic, so don't worry if you sign up, you won't be spammed. But you can chime in there, ask questions, see what's been discussed, see the history and so on. And we had a formal meetings, right? First one in February, that was a hybrid one. We sort of mapped the space and discussed a lot of the solutions out there. And the biggest one we had in Utrecht in May, where for 3 days we were like locked in a room like this and fighting with each other. I linked the notes from all the meetings there if you want to drill through them. That's a lot of content, but if you're curious. And most recently, at the beginning of this month, there was a study group in the front of RustConf where we discussed. There were C++ people there too. Don't assume they were just Rust people. So we're working through it. I think this year was a good year for framing the problems and finding common points. I'm highly optimistic that next year will be the year where we're going to see a bunch of the existing solutions really reach an inflection point and become much more adopted and get more ergonomic. And I'm pretty sure we're going to see some more emerging solutions. So watch the space. If you like this kind of business, I do recommend 2 talks. I mentioned David earlier. So he did a Zengar presentation at C++ Now. It's already online. The link is there. I'll wait. Some people are taking pictures. And if you're really interested about Krubit, this one is not online yet, but it will be soon. It's from Taylor and Tyler from Google, who go in depth about Krubit and design choices and challenges and so on with a bunch more examples. So I very much like this one too, so highly recommend it. With that, I'm very much interested to talk to you about how you see this space and challenges you faced and experiments you've done and how you navigate this space. I can take a couple of questions on the record that we have a couple of minutes, but don't worry, I'll be here until tomorrow. So if you catch me on the hallways and anywhere over food or drinks, happy to chat with you. So feel free to approach me. So yeah, questions.
How do you think about that from the other side? So especially when it comes to stood string, which is self-referential, as you mentioned, some implementations. Would you rather say, let's forbid it to be implemented in a self-referential style such that it can actually cross the boundary efficiently?
So the question for the recording was, how do I see the situation about requiring standard implementations such as standard string to allow for trivial relocatability, as in avoid things like self-referential things and tricks around SSO, so that we have a better interop story, right? For string, it's a very uncomfortable story. I don't know if most people here are aware that we had a similar trauma with standard string a few years back, many years back actually, when we had to support C++ 11 and move semantics, because one of the implementations of standard string was incompatible. It was copy on write implementation, so it was incompatible with move semantics. And we actually had a split there, because that implementation had to provide an alternative implementation that would be move compliant, as C++ 11 compliant. So because of that, we had a long time where you had 2 implementations of standard string and you had to opt into one or the other, as in explicitly. You had to say, oh, I want the old implementation or I want the new standard compliant implementation. That was a very painful 10, 15 years. I don't know how many years been already, but that was a very painful story. I don't know if there's enough appetite for that just for the sake of Rust. And that one was just like selfish. We want it for C++, right? It was like evolving the language. It was needed. You got performance from the move semantic implementation and so on. So there was strong desire to get that thing, and still a lot of people who were profoundly uncomfortable with the split, because they couldn't rely on which string implementation are you using, like, because I need to match it. And we can't just talk to each other if we have different modules assuming different kinds of standard string. It's a nightmare. So again, I don't see a way of how we would fix standard string. And by the way, not all SSO implementations are self-referential. They do different kinds of tricks inside. From my knowledge, the GCC implementation has this pointer to internal, has a pointer in some union. And not all implementations are like that. And even the ones that are, I don't know if there's appetite in the consumers of that implementation to have yet another flavor. And just for the sake of Rust, imagine that, the audacity. Yes. I know Meta did some efforts for the LLV, for the Clang implementation of standard string, to make sure to fix some things, but I don't think it was as invasive as what it would be required for GCC. I don't think I'm the best person to weigh in on this matter, but I suspect there's little appetite to fragment. If that would require just if-defing yet another 10 years. It's not one of those problems that it's technically not doable. Technically, it's easy to solve. It's problem that how do you manage clients, consumers. It goes back to the ABI story earlier. You don't want to lose your clients. Any other questions? Going once, going twice. Okay, so for all the shy people, catch me in the hallways. Thank you.